given by Bill Farrell. Bill is one of our NLSI PIs, and he's going to talk on, and he's from Goddard Space Flight Center. He's going to talk on plasma interaction between bodies in close proximity applications to the Asteroid Retrieval mission at capture and on orbit of the moon, at the moon. Excuse me. Bill, go ahead.
Very good, Greg. I was wondering if you're going to be able to get that whole title. I actually was trying to merge a title and an abstract in a single line. I think I came pretty close.
Nice job.
Okay, yeah, thanks. Well, really, in a nutshell, there's a much simpler title to this, and that is, how are two bodies of about 5 meters in size electrically connected in the solar wind? And the application for this is this recently suggested asteroid retrieval mission, because in fact you're really dealing with bodies about 5 to 7 meters in close interaction. So I'll show you today are some dream models that we put together for part of our Lunar Science Center. We have some modeling up where we show these objects coming together. Really, codes being developed by Mike Zimmerman and Andrew Poppy. So I hope to describe what the ARM mission, this asteroid retrieval mission, is all about, the types of interactions, there's actually 3 of them, and present some preliminary results of what they might look like, how they interact. Now, the key length in a plasma that people talk about is called the Debye length. And basically what the Debye length is if you have a charged object in a plasma, the plasma, which is a conductive gas, will shield the electric field from that object. And the classics, and that's sort of a characteristic length. In the solar wind, it's about 15 meters or so. And, you know, people have studied the Debye sheath for years, and particularly in the area of dust physics. And in particular, if you have a dust grain in a Debye sphere, it'll charge up to a certain level, but if you actually put 2 dust grains in there, they actually will interact, they'll electrically interact, they'll have a mutual capacitance, and in fact, they'll change each other's charge state. If you put a lot of dust grains in there, you now start getting into what's called the collective dusty plasma, and Mihai Hirani and folks like that know all about that stuff. Another example of 2 bodies interacting is an astronaut roving on the surface of the moon. The astronaut is actually in the sheath of the moon, and as the astronaut roves and charges up, he's actually electrically connected to the sheath and will dissipate to the sheath. And Talana Jackson has been working on that kind of thing. But a really interesting study case that was done in 2009 when the shuttle was servicing the Hubble Space Telescope. In this case, the shuttle and the Hubble were initially electrically disconnected, and they came to electrical connection. What was really interesting is that the shuttle is a big water cloud. If you look at that figure there to the upper right hand, this is from data from the late 80s about the shuttle, where she only shows the shuttle ion cloud. It's really just a big comet, if you will. And now it's not really 2 bodies interacting, it's a body interacting with a big gas cloud. In fact, when you think of human systems as really being very gaseous. And so it's really gas and these new photoions associated with the gas that make the electrical connection. So let's see, I'm going to do the next slide here. All right, so what is the ARM mission? Well, in 2012 it was proposed that rather than sending astronauts out to an asteroid, what you'll do is just send out a capture spacecraft, and it'll basically deploy this big bag. They'll capture an asteroid of about 7 meters or so, bag it up, and bring it back into lunar orbit. Okay. Now there's 2 flavors of this. You might grab a whole asteroid is one flavor. The other possibility, can't find a 7-meter asteroid and characterize it fast enough, you might do an alternate plan, which is to go to a much bigger asteroid and pull off a rock, pull off a 7-meter sized object. Either way, a 7-meter sized, they think they want C-class asteroid, should be in orbit around the moon. They're hoping to do it, according to some recent press releases, they'd like to do it by 2021. So it'll be a 2017 launch. And all that is depending on funding, all that. Well, there are really 3 types of electrical interactions. The most obvious one is the asteroid, when it's in orbit around the moon, will be orbiting in the plasma environment created by the moon. The other interaction is at capture time, this capture spacecraft is going to interact with the asteroid itself. And then a third interaction is, of course, when Orion comes to visit with the human crew, and you got the asteroid, and they're going to be around the moon, so that's almost like a three-way interaction. So you got these three different interactions you got to think about here in terms of an electrical connection. Now, if you have just one body, there are really three layers or three plasma interaction regions around an isolated body. The first one, Jasper Helicus talked about earlier today, and that is the plasma wake. You know, when you have solar wind streaming, the front of an object blocks that solar wind. You get this really tenuous wake. For the moon, that can be 1/100th to 1/500th the ambient solar wind plasma. So it can be a substantial structure. And that trails, that's sort of in the dark side of the object. On the front side, because it's sunlit, you're going to get a photoelectron sheath. It's really a bunch of trapped electrons. And in the backside, just above the surface on the dark side, you'll actually get a plasma sheath defined by the electrons, but actually as an object gets smaller and smaller, where the plasma sheath ends and where the wake begins is really kind of a question of some debate. And you kind of get that here. You can see that in the lower right hand. Let's see, I'm trying to find the marker here. I think, is that, I think that, no, maybe that's not it. If you look at the lower left-hand panel, we have, this is a small object. You can see if there's a sheath, plasma sheath, and then a trailing wake, and where one begins and the other ends, it's kind of hard to define. Now, in the case of the moon, actually, the lunar wake goes back about 30 lunar radii behind the moon, and is actually a pretty substantial structure. It's been measured by the WIND spacecraft back at those distances. Now, when you have two objects, though, how they interact and the electric fields you get depends on exactly where they touch. Like, for example, if two solid objects touch pole to pole or terminator to terminator, they're going to have a different electrical effect than if one is coming in from the back through the wake region. And then, of course, you also have to think about the solid body gas cloud interaction when it's a human system like the Orion, which is just a really big gas cloud that photoionizes. And now I got these photoion currents. So it's really a dirty spacecraft if you want to think about it like that. So let's first talk about the asteroid-moon interaction. Let's say they've captured it, now they've released this asteroid, it's orbiting the moon. The sheath, you're not going to fly through the sheath because it's only about a couple kilometers high, but you'll probably fly through the wake region. And as it turns out, this is actually pretty well studied because it's very analogous to spacecraft like Lunar Prospector and Artemis flying through the wake. So for example, I've picked Jasper Helicus and the team at UC Berkeley looked at the spacecraft potential for the Lunar Prospector passing through the wake region. They actually orbiting the moon in general. What they found is that it was on the day side, photoelectron processes would charge the spacecraft positive, but when you got into the night side wake region, you would tend to get more negative potentials, particularly at the edges along the wake flanks. And I guess the reason why I want to show you this detail is that for this kind of process, there's already existing models, and it's been pretty well studied how an object passing through the lunar wake behaves. So I think that one we know pretty well. The one that's going to be really tricky is when the capture spacecraft actually interacts with the asteroid, because here both objects are about the same size. They're actually less than a Debye length out in the solar wind, and when the bag opens up, it's going to outgas. Okay, you're going to have all these gases that are in there, and it's going to outgas. When it outgas, it's going to create a big neutral gas cloud that will get photoionized. Now you got photoion currents to deal with here. And so what we've done is we did models of both the solid gas interaction and the solid-solid interaction. Let me just show you a model here. Here's the gas cloud up here in the upper left-hand corner, and I want to point out here, this is Mike Zimmerman's tree code particle and cell simulation that he's been developing. And it's a 2D plasma simulation. He simulated an ion cloud here. Actually, it's an ion and electron cloud. It's like moving out at basically 300 degrees Kelvin. As it turns out, electrons move out ahead of the ions. And so you end up with an overall outward directed electric field. It actually looks like a positive monopole. He also has a small object here, placed a small object about 5 meters or so, less than a Debye length in size. And actually, as it turns out, this actually looks somewhat like a negative monopole because you get really strong inward directed electric fields, particularly on the backside of the object. And of course, they'll move. We're going to move. I have a series of sequences here where I move the ion cloud in closer to the solid object here. See, here it is passing by. Is it doing it? hold on, I think it may have done something. There we go. Maybe I'm hitting it too fast. So here's another. And my talk seemed to disappear.
Ion cloud.
The ion cloud took it. Let's see. Here we go. We're getting closer. I'm just going to do this slowly now. Okay, now it's gone. There is a rest of the talk. Let me see.
Just about 2 minutes left, Bill.
Okay, 2 minutes left. All right. Let me just see here.
You escape out of there?
I think I'm getting it. Yeah, it's interesting because it's not showing up. All right. Okay, in these 2 minutes, let me just tell you what happens here. I think I can verbally do this. The gas, let me see. The gas, sorry about this, folks. There should be a talk here. It turns out as this, okay, anyway, what ends up happening is as this positive electric field, positive monopole from the ion cloud interacts with the negative primarily monopole from the object, you actually form a dipole. And you actually get a strong electric field gradient. And it's really because you have a gradient in the photo-ion currents from across the object. So what this really suggests is that you're going to get pretty strong electric fields due to this gas current system. All right, and the third interaction in this, of course, is when you have the Orion capsule. Let me see here, and let's see if I can get that. It's all gone.
You do an escape for an escape.
And my apologies, folks. This talk, there's a number of other slides here. But when you actually have the Orion capsule interacting with the object, there'll be a big gas cloud associated with that as well. And that should also be dipolar. So I guess the upshot is, and I apologize if this talk disappeared, but if I only have a minute or two left anyway. Definitely the objects, when they're getting proximity, do have a mutual interaction. In particular, when it's a human system interacting, like the Orion capsule or the Capture spacecraft, it's going to outgas, create a photo-ion cloud. You're going to have photo-ion currents, but the gradients in currents are going to create strong gradients across the object. And I will make sure that I get the talk up there that should be up there. And because it's right here in my notes. You see I got pictures and everything. And we'll get it up online, so if you want to look at it and send me emails about it, we can talk about it. But anyway, I guess that's pretty much it. And I apologize. This is really, I'm kind of mortified here that I lost. At least I didn't fall off the back of the stage, Greg. I got really a league one year. But this is another guy, there really was a talk here.
Thanks, Bill.
Oh, you got the dipole. Some people actually have the dipole on their screen. It's not on this screen. It's not on my screen, but it's on some people's screen. And so maybe that's, so for whatever reason, we somehow lost sync there.
I have a question.
There it is up there now.
Oh, look.
All right, so, okay. Anyway, any questions, I guess?
I have one.
Yeah, Bill, thanks very much. Great talk. Thank you. So, we do have one from Jen Heldman at Ames. Bill, great talk. In your opinion, is there any salvageable science regarding the surface boundary layer of the ARM asteroid after all the disruptions from the interactions with the spacecraft, bag crew, etc.?
Well, that's a really good question. In fact, after interacting, you're actually planting water. And so if you're looking for surface volatiles, you sort of destroyed that experiment. But if you got deeper, it might not be as big an issue. So really it's a question of whether when you bring it back, if you can get inside, get past the superficial layer.
What about actually collecting dust physically?
If it's back, yeah, you could do that. There's no reason.
On the electric field generation.
Would it actually create dust levitation then? These are pretty large fields. They're 20 volts per meter, and that could lock the smaller stuff. Yeah, particularly given its microgravity. Yeah. So, it would change the dust environment as well. You would think. All right, so that's it from this end.
Thanks again, much appreciated.